Okay, so currently now we are in section 6.6. This is the last new section that will be covered on your second exam, section 6.6. 6.6 deals with applications to physics and engineering, and what 6.6 does is it shows how calculus can be used to solve certain physics and engineering types of problems. And we looked last time at some examples. We looked at an example involving the work needed to pull an elevator up 30 feet. We looked at some book examples, one involving Hooke's law, and another example involving work needed to empty a tank. That was actually example 4. Now we're going to look at another problem, and this problem is like one you're going to see in your homework. Section 6.6, you have 2 assignments due this Thursday. I'll try to give you a little time tonight to work on, at least one of them. But let me give you a moment to copy this example down, okay? Okay, I'll give you a little time to copy the picture down. So, I mean, what we have here is a tank, and the tank's filled with water, and we want to find the work required to pump water out of the spout. Now, in this case, the units we're dealing with aren't meters. We're not dealing with meters and kilograms. We're dealing with pounds and cubic feet. Okay, we're not dealing with cubic meters here. So the density of water is 62.5 pounds per cubic foot. All right, and this is a picture of the tank. How many have seen like swimming pools that are kind of like this? I've seen ones like this, like University of Missouri, where I did graduate work. They made a new pool, and it was kind of in this shape. You know, it's kind of like a kind of like that. I don't know. Has anybody ever seen a swimming pool or a tank of water in that kind of shape? Triangular on the side, like the bottom of the tank or the bottom of the pool is. Yep. Okay, Samuel, you've seen that, Samuel?
That's what wave pools look like.
Yeah.
Oh, that's what wave pools looks like. Oh, okay, Maria. All right, Samuel. Like water parks. Oh, okay, Nicole. All right. Well, obviously, I need to get out there a little bit more, don't I? Okay. All right. Let me give you a moment here to copy that picture. This, by the way, this here is just like a layer of water. Okay, this is a layer of water that I'm highlighting. Okay, so, and here is the spout, of course, at the top. Okay, now one moment. It's all good. All right. So just like the example where we had the cable pulling the elevator, okay, and we needed to find the work to lift the elevator 30 feet, and we had to find how much work it took to move the elevator 30 feet, but then we also had to find the work needed to lift the cable 30 feet. And that's the part where the Riemann sum came in, to find the work on moving that cable, because the cable works differently because some of the cable reached, well, it just works differently. So we're going to do this, and what did we do with the cable? We took the cable and we divided the cable up into smaller pieces of cable, and then we actually found an expression for the work needed to bring the ith piece of cable up to the top, and the work is going to vary from depending on what piece of cable you're at, because the pieces of cable are different distances from the top of the building. So similar thing here. We can look at this tank as we can think of this tank as a bunch of layers of water, a bunch of horizontal layers of water. And each horizontal layer of water is a certain distance from the top of the tank. If we're going to pump all the water out of the tank, the spout's at the top. If we're going to pump all the water out of the tank, that's equivalent to taking that tank and dividing it into like a bunch of layers of water, and you know finding the work needed to bring each layer of water to the top of the tank, and then adding up all those work values. It's the same kind of principle. So let me show you here how we'll work this. So okay, we'll go to the solution here. So first thing we need to find, of course, is the volume of the ith layer of water. Okay, I mean, of course, and let me ask you, at different levels of the tank, is the volume of the different levels of water, the different layers of water, going to change? Is it going to be different?
Yes, it's different.
It absolutely, that's right, Leping. It will differ. It will differ. So there's a so the volume of the ith layer of water is dependent how far below the ith layer of water is from the top of the tank. So, you know, if I mean, these volumes, okay, these volumes here, I mean, here again, here's the ith layer of water here. So the layer of water, what shape is it? The layer of water. I mean, if I want to find the volume of the ith layer of water, okay, like V sub I, ith layer of water, what would the volume of the ith layer of water, I mean, what's the ith layer of water look like? Is it a cylinder? Okay, Renaud, you're pretty close. It's a rectangle with some height on it. In other words, if this here, this ith layer of water, if we denote the height by delta x, okay, if we denote the height by delta x, then the volume of the ith layer of water is going to be 10. Hold on here. Let me. Well, that's right, Maria. Like a rectangular prism. Absolutely, absolutely. Let me get this way. Hold on. And use the zoom feature on your right to blow this up if you need to. So you have, I guess it depends on how you look at the tank, but if this is the length is, this is your length. What's your length? How far is your length? 10 feet. That's right. That's right, Renaud. That's right, Jacob. And I'll call this the width. The width, I don't know what the width is, so I'm gonna give that just a variable name. I'll call it A. And then the height will be delta X. So if I'm going to find the volume of the ith layer of water, which clearly, I mean, intuitively you can understand that if I'm going to find the work needed to bring the ith layer of water, to pump that ith layer of water out of the tank, up to the top of the tank and out, I need to know the volume. So what we can do is we can take advantage of similar triangles. Okay, this is what they did actually in example 4 in the book when they were pumping water out of a conical tank. We're going to do the same thing. I mean, here is the side of the tank right here. So you have two triangles. You have one triangle, the big one here, right, that has height 6 feet. If we're just looking at that triangle right here on the side. Okay, so you have height 6 feet, and length 12 feet. Okay, so once again, what I'm doing here, and I'm trying to, this is the side, this is the side here. Okay, and now I have that's a big triangle with height 6 feet and length 12 feet. And then I have this smaller inscribed triangle that has length A, and the distance that this triangle is, or the top of this red triangle is from the top, I denote that by xi. So this means that 6 minus xi, okay, 6 minus xi is going to be the distance you see there. So, all right, let me just, one moment here. Try to make this, should be pretty, one moment, Samuel, one moment. I know you have a question. This is 6 minus xi. So the, you know, for some random layer of water, the layer of water is xi feet from the top of the tank, and therefore it's 6 minus xi feet from the bottom of the tank. Well, we can look at this, then, this red triangle here as having height 6 minus xi and length A. And by similar triangles then, okay, here are the two similar triangles. And so by, you know, what you learned in geometry, the sides of similar triangles are in proportion. So, you know, A over 6 minus I would be equal to 12 over 6. And this is going to allow me to find an expression for the length of that smaller triangle. As you can see here, I have a proportion, and I just solve for A, and that gets me A equals 2 times 6 minus xi, or A is 12 minus 2xi. Yes, Samuel?
So the dimensions of the pump are 10 by 6 by 12.
The big, right, the pool, or the wave pool, I guess, the dimensions, it's 6 feet high, 10 feet wide, and 12 feet long. That's right. So maybe it's like a kiddie wave pool. I don't know. All right. Are there any other good questions on how we got this this value for A? Obviously, A, by the way, is 12 minus 2xi. So obviously, A is a function of xi, and xi is the distance that the layer of water is from the top of the tank. Naturally, the A is going to be a function of that distance. Okay, and my ith layer of water, of course, I kind of made it big so you could see it, but you know, here's the ith layer of water right here, right? This is my, let me try to draw it. This is my ith layer of water. Okay. Well, what do we need to do next now? What should we do next? Now that we know the dimensions for the ith layer of water, we know the length, the width, and the height of this prism, okay, or parallelepiped, or box. Think of it like a very thin box. What do we want to do with these dimensions? What do we want to find for the ith layer of water?
Work.
Well, that we want to get to work. That's right, Samuel. But before we find the work needed to raise the ith layer of water to the top of the tank, or pump the ith layer of water out of the top of the tank, we first need to find
Force.
Well, force would come before that. That's right. But we also need to, before that even, we need to find, begins with a V.
Velocity. Oh, volume.
Well, there's no volume. That's right. The volume. So let's go to that's right, Jacob. That's right, Samuel. So let's find the volume here. All right, may I go to the next page? Okay, excellent. Okay. All right. Well, then here we go. The volume of the ith layer of water is equal to 10 times A times delta X. Okay, because the ith layer of water is 10 feet wide, A feet long, and delta X feet high. And so the A, I already established what A is, 12 minus 2xi feet. And what I do then is length times width times height. That's what this is, length times width. Well, or width, I should say width. Hold on. Width times length times height, if you want. And notice that my units are cubic feet. So when I do this when I work it out, I usually like to include units in my computations so that I know that I'm doing things right, because volume has to be in cubic feet. And we get 100, the quantity 120 minus 20 xi times delta x cubic feet. Now what we need to do is find the force on the ith layer of water. Well, in this case, force is going to be equal to pounds. We're working in pounds. That's our units for force. So what I'm going to do is I'm going to take the volume of the ith layer of water and multiply it by how much 1 cubic foot of water weighs. 1 cubic foot of water weighs 60, hold on. Let me just think here now, one moment here. Hold on, class. 62.5 pounds, that's the density. Okay, just thinking about it, it seems, just looking at this. I mean, that is what the book gives. How many have heard of this? Density of water, 62.5 pounds per cubic foot. How many have maybe seen this in another class? Okay, Maria, you've seen it? Okay. All right, well then, you know, what happens is when we multiply this, I mean, it makes sense. If we have a certain number of cubic feet of the volume of our ith layer of water, and we multiply that volume by 62 pounds per cubic foot, we're going to get the weight of that ith layer of water. And notice that cubic feet simplify out here. They simplify out, and so now we have an expression for the force for the ith layer of water, which is quantity 7,500 minus 1250 xi times delta x pounds. Now that we got the force, next comes work. Because how's work defined, class? How is work defined? Work equals
Force times distance.
force times distance. So we can't compute the work until we get the force. We got the force, now it's time to compute the work. Well, the ith layer of water, gets raised to the top of the tank by getting pumped up a distance of xi feet. If you look back here, I'll just go back here. I'll come back, don't worry. If you look at the picture, okay, here's your ith layer of water right here. Okay, ith layer is right there, and that ith layer of water is a distance of xi feet below the top of the tank. So that's the distance you got to pump that water to get it out of the tank. Question, Marcus?
Yeah, I can't really like tell that well, but what does the delta x represent?
Delta x is the height of the ith layer of water. And I know, I mean, one thing I'll mention, you're used to if you think about like section 6.1 when you were dealing with areas between curves, you know, that delta x would be like a delta y, right? But here we let the vertical axis be delta x. So yeah, that's what this is. The ith layer of water is going to have a certain height to it. Now, naturally, we're going to let those layers of water get thinner and thinner and thinner, so our approximation gets better and better. But it has a, you know, it has a height, and that's called delta x. Good question, Marcus. And so now the work needed to raise the ith layer of water to the top of the tank is equal to this force, okay, times the distance of xi feet. And now our units, we got foot-pounds, which is good. Work is in foot-pounds here. Question, yes.
XI feet is what?
XI feet is the distance that the ith layer of water has to be moved to the top of the tank. Once the ith layer of water is moved to the top of the tank, it's pumped out, and there's no more work for that ith layer. So like when you think about it, when you pump the water out of the tank, the layers of water near the top of the tank are going to take, well, I got to be a little careful because you do have volume also here. But at least in terms of distance, layers of water near the top of the tank have to get pumped less of a distance than layers of water near the bottom of the tank. However, layers of water near the bottom of the tank are going to have a smaller volume in this triangular tank, or you know, this wedge-shaped, triangular wedge-shaped tank. Layers of water near the bottom of the tank are going to have a smaller volume than layers of water at the top. So there's kind of a trade-off here. All right, good,
Well,
good.
it's the distance of the ith layer of water to the top of the tank.
That is correct. That's what this X sub I stands for. And again, if you look at the picture, that's this XI here, Samuel.
Oh. Okay, I get it. Thank you.
Okay, all right. You're welcome. All right, so now we got the work expression for the work needed to raise the ith layer of water to the top of the tank. So then the total work, which I'll call just W, that's going to be the Riemann sum, where you add up all the ith layer, all the work, each piece of work for the ith layer of water to raise that ith layer of water to the top of the tank. And then you'll let n go to infinity. So in the limit, you look at a lot of very thin layers of water. And then what's going to happen is you're going to get an integral. The Riemann sum becomes an integral. It's going to become this integral. Audra, question?
When you say the total work, does that mean the total amount of work to raise all the water?
That's correct. That's the total amount of work to raise all the water out of the tank.
Okay, thank you.
You're welcome. You're welcome. All right. Are there any...
0 to 6 is the height.
Well, let's talk about that. First of all, let me just say one thing here. We'll talk about that, but let me just show. So Renaud, the layers of water in the tank, and I can remember your question, Samuel. Don't worry. You'll remind me though if I don't remember it. Okay. But you see well, now actually, hold on. I think I made, no. Let me ask you this, Renaud. Let me ask you this. So you see the picture here at the top, right? You see the picture there? And you see that ith layer of water. I'll call that ith layer of water 1. Okay, now let me draw another ith layer of water here near the bottom. Okay, a second ith layer of water. I'll call that layer of water 2. Now, which layer of water has more volume? Layer 1 or layer 2? Layer 1 has more volume. Okay, so in that sense, the first layer is heavier than layer 2. So the first layer of water, in that sense, it's going to affect how much work's needed. it's harder, heavier, a layer of water that's heavier requires more work to lift. But which layer of water is closer to the top of the tank, layer 1 or layer 2? Layer 1. So layer 1, even though it's heavier than layer 2, layer 1, it's less of a distance to pump it out of the tank. So that in that sense, it makes the work less. So you have this balance between how much volume the ith layer of water has, and how far down it is from the top of the tank. And that's why the work needed to raise the ith layer of water, you notice it's a function of xi. It's a function of xi. Okay, and I mean, what the work is, it's a product of the force or the weight of the ith layer of water and the distance to raise that ith layer of water to the top of the tank. Both to do this problem properly, we have to have both. Renat, does that help you feel more comfortable? Good. All right, you're welcome. And okay. And Samuel, you were asking now about these limits from 0 to 6. Okay. Well, first of all, let me ask: is everybody okay that this Riemann sum? The Riemann sum is just the Riemann sum of these pieces of work here. So if we Riemann sum, if we put a sum in front of that, do you agree then that they would go to this integral? Are we okay with that? Maybe give me a thumbs up if you're okay. Okay, Jacob's seeing that. Leping, okay. I mean, are there Jacob and okay, many of you, excellent. Now, thank you, and Baraka, and thank you. And now Samuel's wondering about these limits. So the limits I have from 0 to 6. Okay, how am I getting these limits? Well, if we go back to the picture, the tank is full of water. This tank is full of water. So this is different than the example 4 in your textbook. That tank of water wasn't full of water, okay? But this tank of water is full of water. So let me ask you this. The top layer of water here, about how many feet does the top layer of water have to be moved to get pumped out of the tank, the very top layer of water? How many feet does that have to be lifted? The very top, at the very top.
6 feet.
Well, let me ask you this. The layer of water at the bottom of the tank, here's the spout, right? Here's the spout at the top of the tank. The layer of water at the bottom of the tank has to get lifted how many feet to get moved out of the tank, to get pumped out of the tank? 6 feet, right? That's right, Jacob, 6 feet. So that's one of the limits, right? 6. What about this layer of water at the top of the tank? That basically gets moved 0 feet. It's basically almost ready. It's at the top of the tank. It just gets pumped out right away. So that's 0 feet. You see what? Samuel, you're comfortable with that? On those limits?
So the upper limit is applies to the bottom of the tank, and the lower limit applies to the
well.
top of the tank?
So let's remember what a good question. These limits here, 6 and 0, are x limits, right? Because we're integrating with respect to x. X is defined. X is defined, remember, as the distance. I mean, it's x sub I in the Riemann sum, but x is the distance that the layer of water is from the top of the tank. Well, the layers of water are going to vary from layers of water will be anywhere from 6 feet below the top of the tank, 6 feet down, to 0 feet, to the top of the tank. I mean, the layers of water are going to range from being 6 feet below the top of the tank to 0 feet below the top of the tank. X sub I is the distance the layer of water is from the top of the tank. And that's why the limits go from 0 to 6. Nathan, question?
Yeah, I have a question about the total work and the units. You have delta X in the equation above that to make it foot-pounds. So
Yes.
how is the last equation also foot-pounds?
Well, what you're doing is this integral is derived from a Riemann sum, where you're adding up a bunch of pieces of work. Every piece of work has units that are in foot-pounds. So therefore, the integral, which is like the exact amount of work, okay, is going to be in foot-pounds. Does that make?
Yeah, I understand that, I think. I'm just wondering, the delta X certainly is not in that bottom equation, so.
Well, what happens though? Okay, hold on. All right, so good question. Let me show you this here. One moment. Hold on. Let me put in an additional. One moment. So the work is going to be the Riemann sum from 1 to n of 7,500 xi minus 1250 xi squared delta x. Okay, and you do you agree? You're okay that this expression here is for the ith piece of work, to bring the ith layer of water to the top of the tank, to pump that ith layer of water up to the top of the tank. You're good with that so far? All right. What we're going to do, and the units are in foot-pounds. That was established. Now what we're doing, of course, is we're going to take the limit as n goes to infinity. And when we do that, what does this Riemann sum become?
Integral.
An integral. Okay, the limits are going to be from 0 to 6. Delta x becomes dx. And what goes in here? What goes in there? What's the integrand?
Yep, 7,500 xi minus 1250.
Or x, right, minus 1250 x squared. Okay, does that help you feel a little more comfortable, Nathan?
Yep.
Okay, good. I mean, this is what section 6.6. They're basically taking Riemann sums. They're getting Riemann sums for the work, and then they turn into integrals in the limit. So, okay, now, hold on here. Let me bring back the thing here. Okay, so that gets us then here. That gets us here. And now we just integrate that. We just integrate that. And it's a simple integral to do. And in the end, you're going to get 45,000 foot-pounds. And that's your answer. And this is, you know, this is important. I mean, this is engineering applications, and you know, of course, you know, it's coincidental that we're covering this section at the time when that condo building in where was it, Surfside, Florida, I believe, collapsed. How many saw the video of that? I think they had it on CBS. Very sad to see it. So okay, many of you have seen that. Sophie's seen it, and quite a few others here. But you know I mean, they're going to have to find out the cause of that. I don't know if it's a sinkhole issue but from what I've been hearing, the condo, you know, there was deterioration there, and but this. I'm just trying to say that engineering is important, you know, and they had engineers, I believe, survey the building, and they found out that it needed a lot of repairs, and you know, so all this knowledge you're learning is extremely useful, okay, and getting the right answers is extremely useful. Extremely useful. I oftentimes think of examples. I haven't seen this too much lately, but I know, like when I was younger, it was a condo building where they had a balcony, and there were a lot of people on the balcony. There were a number of people on the balcony, but you know, the balcony collapsed, and then it dropped on some other balconies, and you know, some people were like really injured, but you know, I say to myself, well, did the engineers design that balcony properly for, you know, the number of people that could be on that balcony? You know, and these are the kind of things, you know, that you know, we have to think about how important engineering is, and getting the right answers. And that's one of the reasons I stress it's important to get the right answer. And if you don't get the right answer, like on an exam, figure out what you did wrong and then try again to get the right answer. Very important. All right, are there any questions before we move on? Okay, let me stop the recording.